Have you ever looked up at the sky and thought, that's it, just blue, maybe some clouds, maybe stars at night? What if I told you that above your head, right now, there are storms larger than continents, rivers of air moving faster than hurricanes and forces so subtle, they weren't even confirmed until 2024. Every breath you take, every weather event you've lived through, even the fact that Earth can support life, it all hinges on a fragile, invisible system that's changing in ways we're just beginning to understand. This isn't just a science lecture. It's a story about survival, about mystery, and about how something we barely notice, our atmosphere, holds secrets that could shape our planet's future. From the ground up, Earth's atmosphere might seem like a simple blanket of air. But in truth, it's more like a multi-layered fortress, with each level playing a different role. Most people would point to the hazy layer we see during a sunset and say, that's the sky. But what you're seeing is just the first of 5 layers. We start at the troposphere, where all life lives and weather forms. It's surprisingly thin, just 7 to 20 kilometers high. Above that is the stratosphere, home to the ozone layer and where commercial jets cruise. Then comes the mesosphere, where meteors burn up. Next is the thermosphere, where the auroras dance and the International Space Station orbits. And finally, the exosphere, the uppermost region that blends into space, extending thousands of kilometers. Each layer marks a reversal in temperature trends. In the troposphere, it gets colder as you go up. In the stratosphere, it gets warmer due to ozone absorption. The pattern continues, alternating in a rhythm of heating and cooling driven by complex physical processes. So why is the sky blue? And why do mountaintops remain snowy even in summer? The answers lie in how sunlight interacts with Earth's surface and atmosphere. Sunlight delivers energy in the form of electromagnetic radiation. Surprisingly, the air around us isn't very good at absorbing this energy. Most of it passes right through. But the ground, especially dark surfaces like asphalt or forests, absorbs that energy and heats up. That heat then gets transferred to the atmosphere through conduction and convection. Conduction happens when the warm ground transfers heat to air particles in contact with it. Convection takes over as these warm particles rise, expand, cool, and eventually sink again. This creates massive invisible cycles of air, like boiling soup in a pot. One of the best real-life examples of this can be felt in cities like London, which are consistently a few degrees warmer than surrounding rural areas. Why urban surfaces like roads and buildings absorb and release heat much more effectively, creating what's known as the urban heat island effect. This vertical circulation isn't just local, it scales up globally. Enter the Hadley cells, gigantic loops of circulating air found near the equator. As warm air rises, it flows north and south, cool sinks, and returns, creating massive belts of weather activity. These cells are responsible for the tropical rain belts, the jet streams, and even the positioning of deserts like the Sahara. In places where air descends, such as around 30 degrees latitude, it creates dry zones. That's why deserts often form in these regions. Take the example of the jet stream, a river of wind that can travel over 400 kilometers encircling the planet. These narrow bands of strong wind are crucial to weather forecasting and airline routes. They also act as barriers, keeping cold air from rushing too far south until they break. We've long known about Earth's magnetic field and its role in deflecting solar radiation. The ozone layer too protects us by absorbing ultraviolet light. But in 2024, scientists finally confirmed something that had been theorized for decades: the ambipolar electric field. This field, though weak, just half a volt, helps regulate the polar wind and escape of charged particles from our upper atmosphere into space. Without it, Earth might have ended up like Venus, a scorched, barren wasteland. Venus likely lost its water due to a much stronger electric field about 10 volts, that pulled heavier particles like oxygen into space. Earth's weaker field may have been its salvation. Noctilucent clouds, aspiratus waves, upside-down rainbows. These aren't fantasy, they're real phenomena happening high above us. Noctilucent clouds, for instance, form in the coldest part of Earth's atmosphere, the mesosphere, during summer. They reflect sunlight long after the sun has set. They are rare, beautiful, and eerily symbolic of how interconnected our atmosphere is. Then there are aspiratus clouds, which look like the sky turned into a stormy sea. First photographed in Iowa in 2006, they were only officially recognized in 2017 thanks to citizen science. These clouds are born from atmospheric gravity waves, convection, and unknown interactions, reminding us we're still discovering new parts of the sky. Imagine sitting in an airplane cabin and seeing a glowing orb float silently down the aisle. Sounds like a dream. That's what a University of Kent researcher reported in 1963. Ball lightning is one of the strangest weather phenomena ever reported. Scientists have tried to recreate it in labs with some success: plasma bubbles, silicon vapor reactions, and even quantum simulations. But the phenomenon remains largely elusive. Whether it's real or a series of hallucinations triggered by magnetic fields, ball lightning straddles the line between myth and measurable science. Now imagine a wall of wind encircling the Arctic, a jet stream moving so fast it traps icy air. This is the polar night jet, a fortress of air that keeps the North Pole's chill contained. But when this jet stream breaks, the cold escapes. In 2009-2010, the UK was paralyzed by a deep freeze. In 2019, parts of the US hit 50 degrees during a polar vortex event. These aren't isolated flukes. The jet stream buckles under pressure from warming oceans, mountain ranges, and even El Niño. Sometimes it rebounds, sometimes it doesn't, and the consequences can be deadly. Earth is leaking. Every second we lose 3 kilograms of hydrogen, 50 grams of helium, and small amounts of oxygen to space. This is part of a natural process, but over billions of years it has real consequences. The ambipolar field again plays a role. It gently accelerates light ions upward without heating them. That's why the loss isn't catastrophic, but it's steady, relentless. Venus lost its water, Mars lost its atmosphere. Earth is holding on, but barely. Our atmosphere is not just air, it's a guardian, a storyteller, and a ticking clock. It filters light into a blue sky. It shields us from solar storms. It gives rise to cloud cities and auroras. And it whispers to us through strange signals, rare clouds, and electric mysteries that we're only beginning to decode. So next time you look up, pause. Not just in wonder, but in recognition. That sky is working overtime to keep you alive. And maybe, just maybe, we should start listening.